So let's say we're trying to do a least squares process to build a linear model with a large set of variables. So say we have a large set of predictor variables. I will call those x1, x2, x3, up to xn. So in the example we talked about last time, maybe x1 is the square footage of a house, x2 is the number of bathrooms in the house, x3 is the size of the lot, x4 is the number of bedrooms, x5 the number of doorknobs. Some of them are going to be useful and some of them are not going to be all that useful. So these are our predictor variables, and we'll just let y be our response variable, our output variable. And the goal is to build a model which picks just the important predictor variables and leaves out what are called the noise variables, variables that don't tell you very much about the response variable, but your output variable. So we almost certainly square footage will be in, and number of doorknobs will be out, and size of the lot will probably be in, and number of light switches will probably be out. There are two problems. Two difficulties. And that is one we talked about last time. If n isn't very small, if n is a medium or large number, and so say n is 30 or 40 or 50, not an unreasonable amount, n could be 1,000. If n isn't small, the number of subsets of the n predictor variables is 2 to the n. It's 2 to the n even if n is small, but if n isn't small, that's huge. If n is 10, if there are 10 predictor variables, the number of subsets of 10 things is 2 to the 10th. That's 1,000 already. That's not that bad. If n is 20, it's 1,000,000. If n is 30, it's about 1,000,000,000. If n is 40, it's already about 1,000,000,000,000. These numbers are getting big fast. And by the time n gets to, say, something like 100, there's just no way. Secondly, we saw last time that r squared was equal to 1 minus RSS over TSS, and I'll refer you to a previous video to remind you what RSS is. Remember, RSS is just the residual sum of squares, the vertical distance between where the data point is and where the model predicts it is. You take those errors, square them, and add them all up. TSS has nothing to do with the particular line or plane or whatever your model looks like itself. That's just the vertical distance between where the point is and the average of all the points. And you take those values, you square them, you add them all up. So this has to do with the model, this doesn't. Now the problem is, when you add a noise variable, this doesn't get worse. R squared doesn't get worse. It might get marginally better, but it doesn't get worse. So if you were hoping that we could use R squared to decide which of these things were noise variables and which of them were good predictor variables, it's not so great. Now what's true, and you might be able to come up with something along these lines, is if you add a good predictor variable, so you say you have a model, you add another variable that's a good predictor variable, this will probably increase more than it would if it were just a noise variable. And you might be able to come up with some sort of reasonable algorithm in your head to use R squared. But what we're going to talk about, so I'm going to tackle this second problem first. So instead of R squared, we use something called adjusted R squared. So R squared is just this. Adjusted R squared is going to be the residual sum of squares, RSS, over n minus d minus 1. And I'll explain, you already know what n is. That's the number of total variables available to you. I might as well just tell you what d is right now. D is the number of variables you're using. And the bottom, so obviously I have a compound fraction here. The bottom is TSS over n minus 1. Okay, so I'll talk about that in a second. Let me first go back and talk about R squared. So to maximize R squared, since TSS has nothing to do with the model, all you want to do is make this term as small as possible. So remember, R squared bigger is better, means better fit. So if we want to maximize R squared, we want to make this term as small as possible. TSS doesn't change based on the model, only RSS does. So to maximize R squared, that's the same thing as minimizing the residual sum of squares. That should make sense. If those, remember the residual sum of the squares is the sum of the squares of the errors between the actual data points, their y values, and the y values that are predicted by your model, your line, your plane, whatever. And so if you can minimize these, it certainly makes the fit better. So to maximize this, so remember I said that n is the total number of variables available, d is the number of variables in use. TSS doesn't change on the model, and certainly n minus 1 doesn't because n doesn't. N is the total number of variables. You have nothing to do with that. You're handed, this big spreadsheet. It has 1,000 columns. N equals 1,000. Each column is going to be, one of the columns is going to be the square footage. One of the columns is going to be the, area of the lot, whatever, if we're talking about the houses. But you have nothing to do with that. All you can control is which variables you're choosing, and d is the number of variables you pick. So you can't do anything about this. Oops, adjusted R squared isn't this, it's 1 minus this. Sorry about that if you're taking notes, it's 1 minus this. So we've just replaced RSS with RSS over n minus d minus 1, and TSS with TSS over n minus 1. But be that as it may, and you can pause the video and correct my silly error, it's 1 minus. You can't do anything about that. TSS, nothing to do with the model. N minus 1, you can't change that because you're just handed a certain number of variables. What you have control over is the top here. Which variables are you choosing? So to maximize adjusted R squared, what you want to minimize is the numerator here. RSS, hopefully you can see this when I get out of the way, over n minus d minus 1. RSS over n minus d minus 1. Now I said before that even when you add noise variables, RSS is going to get smaller. Even it might not get much smaller, but it's certainly not going to get bigger. So R squared is going to get bigger even if you have noise variables. But the thing is, what we have now is a denominator. And if we want to we're trying to make this as small as possible. So it's possible that if I add a noise variable, RSS might get marginally bigger, but D also gets 1 bigger. If I add 1 more noise variable, d is going to get bigger by 1, which is going to make the denominator smaller. If the denominator of a fraction gets smaller, the whole fraction gets bigger. So if we're trying to minimize this and I add a variable, I'm going to have to add enough. I'm going to have to, if I want r squared to get actually bigger, which I'm trying to do, I want my adjusted r squared to get bigger, then the numerator is going to have to increase by enough so that the fact that d gets bigger by 1 when I add one more variable makes this whole thing not get. Sorry, I take it back. Sorry. If I add one more variable, I want the numerator to decrease by enough such that the fact that the denominator is also getting smaller doesn't counteract it. So we're going to use this adjusted r squared. So instead of RSS, we're going to use RSS over n minus d minus 1. And instead of TSS, we're going to use TSS over n minus 1. As I said, maximizing adjusted r squared is the same as minimizing this. The n minus d minus 1 in the denominator of the numerator, sorry about that, it's a compound fraction here, means that there's sort of a penalty for taking an extra variable if that variable doesn't really add too much to your knowledge of the response variable. Okay, so we've sort of dealt with problem number 2. Problem number 2 is that even when I add a noise variable, it doesn't make r squared worse. It doesn't make r squared smaller. If anything, it might make it a tiny bit bigger. But if I add a noise variable, then adjusted r squared is not going to get better. If I add a good variable, adjusted r squared is going to get better. Adjusted r squared is going to be bigger. In other words, RSS over n minus d minus 1 is going to get smaller. Now, back to the first problem. I can't just go ahead, if I have 100 variables, I can't just go ahead and try all 2 to the 100 options. It is too big. So we need some sort of algorithm which is going to hopefully get us a pretty good idea of what we're doing. And let me outline a possible algorithm for you. It's not hard. Start off with no variables at all. Then, Start off with no variables at all. Then try the variables one at a time. So we'll try just x1. We will try just x2. We will try just x3, all the way up to xn. See which one of those. So we're just gonna have one variable and our response variable. In other words, we will have an honest to goodness straight line for each of these. In the first case, we will just have our horizontal axis will be x1 and our vertical axis will be y. In the second case, our horizontal axis will be x2, our vertical axis will be y. In the third case, our horizontal axis will be x3, our vertical axis will be y. And for each of those, you can compute an adjusted r squared and see which one of them is the best. Say x3 is the best. So x3 is the best one. It has the best adjusted r squared. Now, try n minus 1 new models. Try taking x1 and x3. Well, let me say x3 and x1. Try taking x3 and x2. Try taking x3 and x4, and so on, all the way up to x3 and xn. So now we have 2 parameter models. So now for this one, we are going to have like 2 horizontal axes. One is going to be x3, the other is going to be x1, and we still have y. And then here we'll have x3 and x2, and we'll still have y on the vertical axis, and we'll build a plane. And for each of those, we will compute the adjusted r squared, and so on. And we will take the best one, whichever one it turns out to be. And then for each of these, we'll try adding each of the other variables individually, and we'll just keep going and adding one variable individually and keep picking the best ones. And then of each of the ones we've circled here, so the one with 1, the one with 2, the one with 3, the one with 4, we'll pick the one with the highest adjusted r squared. Is that the best of all 2 to the n? Who knows, but it's a pretty good idea. It's a pretty logical way of trying to get a pretty good one. It may not be the very best one, but hopefully we do pretty well. We could also start, this was sort of a bottom-up approach, starting with no variables and adding them one by one. We could have started from the top. We could have started with using all the variables, x1, x2, x3, all the way up to xn, and then pulling one out. And try pulling them out one at a time. First, get rid of x1, then get rid of x2, then get rid of x3, and try all those n cases and see which one has the highest adjusted r squared. Then from that one, pull the remaining ones out one by one. And instead of going from the bottom, this time we're going from the top. And then we have a tree that's sort of grown from the top. Pick of all of these, at all these levels, you'll have one with all n variables, one with n minus 1 variables, one with n minus 2 variables. See which one has the highest adjusted r squared. I'm sure with a little bit of thought, you could come up with other variations on this. Is it perfect? No. Is it pretty good? Yeah, probably.